We're going to talk about the basics of energy, right? How energy is used in chemistry. And when we talk about physics, physics and chemistry pretty much merge at this point when we're talking about energetic analysis, okay? So there's a couple of things you want to know about energy. There's two basic kinds of energy. First energy you should know about is potential. And the second kind of energy that you should know about is kinetic. Kinetic energy is the energy that's actually easier to describe. It's the energy that, or it's the description of something that is in motion. Okay? Matter of fact, kinetic energy can be measured. Okay, so here's energy kinetic. If you look at 1/2 of the mass of an object, there's the mass of the object, and the velocity of the object as well. The book uses U. In all of my life I've used V, so it's mv squared at this point. All right? So energy is equal to 1/2 mv squared. So anything that's in motion, anything that has a velocity, is going to have energy associated with it. All right? Remember, there's two different types of motion that you get with physics. All right? And the motion that you get, there's velocity, and that's the speed of an object. Okay? So how fast something is moving is velocity. The second half of that is going to be acceleration. How fast is it accelerating? Okay? Things in space move at a certain velocity. You have to apply energy to get them to accelerate. Okay? Force equals mass times acceleration. How fast you're accelerating an object depends upon the amount of energy that you're applying to that object. Okay, velocity is just the base speed of something. All right, so velocity, how fast something is moving through space, right? All right, so that's just the basics of kinetic energy. Everything in motion is going to be kinetic energy. Energy terms that we can derive from this type of relationship, okay? Obviously, we've got speed, so we're going to have some kind of pressure. And pressure comes from the atoms with a certain speed hitting a surface. And they keep hitting that surface, they're pushing against that surface, right? So each time they hit that surface, they're exhibiting a pressure that's just upon that surface. Okay, so that's one part of kinetic energy. Temperature. Everybody says how hot something is. Temperature is not a measure of how hot something is. Strangely enough, it's a measurement of how fast molecules are moving within a certain object. Okay? So temperature is a measure of actually the kinetic energy of atoms, molecules, compounds, whatever you're measuring. If I put a thermometer into water and it's boiling at 100 degrees C, what that's relating to me is that those molecules are representing a speed at which water boils. Okay? It also means don't stick your hand in it because it's hot. So that's kinetic energy. Potential energy is a little bit more esoteric. It's a little bit more abstract. Okay? It's stored energy. So potential, another way of looking at it is stored energy. So if I lift up this eraser, right, the higher it goes, the more potential energy I'm storing inside of it. Okay? Because if I drop it from here, it only drops a certain amount, and it only has a certain amount of distance and energy that's being imparted because of the acceleration of gravity. Now, I drop it higher, it's going to make a louder noise. There it is, unless it lands on the felt side, right? Of course, that's the way it's going to work in this class. As I go to a higher position, I'm storing more energy inside of this object. I have to exhibit my energy on this to push it to a higher position. Okay? So at that point, what happens is that the stored energy is going to be imparted from me to this object. Okay? That's things like taking a bowling ball and taking it and putting it on top of a mountain. Okay? But unfortunately, when we get to chemistry, we're not talking so much about bowling balls. But what we're talking about are atoms, right? The best place that we can see potential and stored energy is going to be in bonds of molecules. Okay, so this location, potential energy, stored energy, is found in, oh look, Denmarkerville. Bonds. All right? Now that's where we're going to find those types of relationships. Potential energy in chemistry is another way of looking at it, is to say there's a certain electrostatic interaction between atoms, because there's going to be positive charges and negative charges that are there, especially with the electron clouds when they start interacting. Okay? So potential energy, electrostatic energy, so here's electrostatic energy. And this one is going to be equal to the two charges, essentially, Q1, Q2, right, and the distance between the two. If you know anything about physics, this looks very familiar, because this is going to be the gravitational attraction, okay? Two massive objects, they experience gravity, and there's a distance between them. The closer they are, the more gravity exerts motion upon these two as they approach each other, okay? So electrostatic energy is similar as far as charges, as these two things get closer together. And this energy is kind of stored. Now, last thing I want to talk about with this little section, because energy is a huge part of what we talk about, we talk about it in great detail. Last thing I want to talk about is a law of science, and that is that energy cannot be created or destroyed. And there's a corollary here. And I'm going to pull out Einstein, okay? Because everybody loves Albert Einstein because he had great hair. Yeah, unlike mine, yeah, right now. I got mugged by a lawnmower, check that out. But energy cannot be created or destroyed. And when I look at Einstein's famous equation, E equals mc squared, what this stands for is energy is equal to mass times the speed of light squared. It's a nuclear equation, because there's small changes when you go through nuclear fission and nuclear fusion. There's a small destruction of mass there. That mass is not really destroyed, but rather transmuted into energy, which is then released in these nuclear processes. So when the nuclear process goes on, a certain amount of energy is going to be released. Okay, why do I show this here? Because there's a relationship. This is a constant, and these two things are variables, but they're interrelated variables. Okay, I can't have energy without mass, mass without energy in this equation. In the corollary, the reverse is going to be true. So if I have energy, it comes from mass. Mass is not really being destroyed in a nuclear process. It's being transmuted into energy. The flip is possible as well. I can take energy and turn it into mass. How do we do that? I don't know, but they do it on Star Trek. That's the fundamental things of the replicators, right? You can take energy and turn it into stuff, like a chicken sandwich. Okay, but here, energy equals mass c squared. We can only go one direction with this. We don't know how to make mass yet. Okay, sorry guys, we can't make mass yet. But note that energy and mass cannot be created or destroyed. This is a conservation principle. By conservation principle, that means that we're conserving energy and mass that are associated with the universe. We just can't get rid of it. The energy and mass in the universe is going to be constant.